All right, we are on the last section, section 8.5, power. Let's look at the figure. This is actually a return to example, I think it's example 7.7. And in the figure, a man rolls a refrigerator up the ramp into the truck, but the man's not convinced that the work is the same regardless of the ramp's length. So he sets up a longer ramp with a gentler rise. The man does the same amount of work because it's MGH, the change in potential energy. The man does the same amount of work as someone using a shorter ramp. It takes longer to do the work because he has to move the refrigerator over a greater distance. Work is done on both ramps. The work done on both ramps is the same. Something is different. Well, what is different is the time interval during which the work is done. So the time rate of change of energy, that is the time rate of energy transfer, is called instantaneous power and is defined as power is equal to dE dt, the change in energy for a time interval. The focus is on the work as energy transfer method. Note that the power is valid for any means of energy transfer. If the external force applied to the object, modeled as a particle, and if the work done by this force on the object in the time interval, delta t, is W, then the average power during this interval is average power is equal to the work divided by the time, delta time, work divided by the delta time. The average, for example, in the figure, the same work is done rolling the refrigerator up both ramps, but less power is required for the longer ramp. So let's, the instantaneous power is the limiting value of the average power as delta t approaches zero. dW is the infinitesimal value of the work done. dW is equal to the force times the little distance, the small portion of distance. For a constant force, the instantaneous power is dW over dt, which is force, times dr dt, which is equal to force. Dr dt is equal to velocity, so it's force times velocity, where the velocity is equal to dr dt. Okay, the units of power are the watt. The SI unit of power is joules per second, joules divided by seconds, and it's equal to a watt. 1 joule per second is equal to 1 watt, and it's named after James Watt. The unit of power in the U.S. customary system is horsepower. So 1 horsepower is equal to 746 watts. The unit of energy or work is defined in terms of unit power is 1 kilowatt hour, which is 10 to the 3 watts times 3,600 seconds. So that's 3.6 times 10 to the 6 joules. It's the energy transferred in 1 hour at a constant rate of 1 kilowatt. It's the amount of energy represented by 1 kilowatt is this 10 to the 3rd watts times 3,600 seconds. A kilowatt hour, the unit is a unit of energy, not power. When you pay your electric bill, you are buying energy, an amount of energy transferred by electrical transmission, usually expressed in kilowatt hours. An example is the electric bulb rated at 100 watts. In 1 hour of operation, the energy transferred by electrical transmission is 3.6 times 10 to the 5th joules. That would be, I think, 360 kilojoules. Okay, now on page 201, there's a pitfall prevention that probably is important to note. It's pitfall prevention 8.3. W, italicized, and watts. Do not confuse the symbol W for the watt with the italic symbol W for work. Also remember that the watt already represents a rate of energy transfer. So watts per second does not make sense. The watt is the same as joules per second. So it already has time involved. Let's look at an example. An elevator car has a mass of 1,600 kilograms and is carrying passengers having a combined mass of 200 kilograms. So the total mass is 1,800 kilograms. A constant friction force of 4,000 newtons retards its motion. Part A, how much power must a motor deliver to lift the elevator car and its passengers at a constant speed of 3 meters per second? Now the motor must apply the force of magnitude T tension that pulls the elevator car upward. Now the friction force increases the power necessary to lift the elevator. The problem states that the speed of the elevator is constant, which tells us that the acceleration is equal to 0, so that the tension in the cables is equal to the mass times G of the elevator and passengers, and along with the friction force. We model the elevator as a particle in equilibrium. Remember, the fact that the acceleration is 0 does not mean that it's not moving. It just means it's moving at a constant velocity. Okay, the free body diagram specifies the upward direction as positive. The total mass M of the system, the car plus the passengers, is equal to 1,800 kilograms. Using the particle in equilibrium model, apply Newton's second law to the car. The sum of the forces in the y direction is equal to the tension in the cables minus the friction minus mg, which is equal to 0. So the m there is the 1,800 kilograms, which is the car and the passengers combined, and g, of course, being the 9.8 meters per second gravitational acceleration. Now let's solve for t. T is equal to mg plus f. Note that t is in the same direction as v, and we find the power. So P, the power, is equal to T dot V, and here, there is no theta, so all we get is TV, the tension times the velocity, not television. TV, the tension times the velocity, and that's equal to mg plus f times the velocity. Now substitute the numerical values, and you get 6.49 times 10 to the 4th watts, or 64.9 kilowatts. Okay, let's look. What power must the motor deliver at the instant the speed of the elevator is v if the motor is designed to provide the elevator car with an upward acceleration of 1 meter per second squared? Now, in this case, the motor must apply the force of magnitude T that pulls the elevator car upward with an increasing speed. We expect that more power will be required to do that than in part A, because the motor must now perform the additional task of accelerating the car. In this case, we model the elevator car as a particle under a net force because it is accelerating. Now, net force. Now, if the net force equals 0, then it's constant velocity, no acceleration. But if there is a net force, then there has to be an acceleration. Now, using the particle under a net force model, apply Newton's second law to the car. I'm sorry, I skipped that explanation of part B. You can read it there. Now let's go on. We apply Newton's law to the car. The force in the y direction equals the tension minus the friction minus the mg equals the mass times acceleration. Let's solve for t. T equals the overall mass times the acceleration of the elevator plus the gravitational acceleration plus the friction. Obtain the required power. Power equals the tension times the velocity equals the tension is dictated above, m times a plus g plus f times v. That's the power. Now let's substitute the numerical values where v is the instantaneous speed of the car in meters per second, and P is in watts. So to compare with part A, let V equals 3 meters per second, giving a power as shown, which is larger than the power found in part A as expected. That's 70.2 kilowatts as opposed to, what was the last one, 69.4? Yeah, 64.9 kilowatts for the last one. This one took 70.2 kilowatts of power. Okay, this ends chapter 8.